So, alternative energy. We're going to be talking today about wind, solar, hydroelectric, geothermal, and nuclear, and maybe another if I forgot. So, what we have to remember is that for all kinds of activities that you would want to do in the modern world, whether it's transportation or just leisure or real work, everything from watching the TV to driving your car to doing everything except going for a walk depends on energy, and we use fossil fuels as the go-to method for powering everything. The TV is powered by the electric grid, which runs off of coal and natural gas in this country for the most part. And we do that because, as we discussed in the last lecture, fossil fuels are cheap, they're plentiful, they're energy dense, they're easy to import and export, and they are reliable. They'll produce energy all day, every day, and indeed they do. The goal is to either create mechanical power, which is what your car engine does by burning gasoline, or to make electricity, which is what burning coal and natural gas also do in our electric generators. Now, alternative energy forms, they're used pretty much exclusively for generating electricity. Alternative energy cannot give us mechanical power in most cases. So there's no solar powered car. That just really isn't possible. There's no uranium powered car. Although Ford did obsessively try to develop a car that ran on nuclear energy in the 50s and 60s. You can look that story up for yourself. So for this foreseeable future, alternative energy can solve many of our electricity needs, but not our transportation needs. That just isn't going to happen. The electric car, I don't believe, should be considered alternative energy because while maybe it doesn't directly run on fossil fuels, it runs on a battery. Those batteries are going to be charged by fossil fuels. So a car an electric car battery, to charge one of those with like a rooftop installed windmill or rooftop installed solar panels would take so much time that's just not practical because most of us have to drive every single day. And so those just aren't going to meet the need. But our electric grid, which runs mostly, like I said, off of coal and oil and natural gas, is going to be able to do that. Because ultimately the source for that electric car comes from fossil fuels. But anyways, the most electricity intensive device in your home is the air conditioning, and if you have electric heaters, the heating. The next most intensive would be natural gas. So in my home, I have central air. There aren't floorboard heaters in the rooms in my home. So the vents either blow cold air from the air conditioning, which uses electricity. Obviously, natural gas doesn't use electricity, but I can show you my utility bill. In the winter, the electricity usage goes down, but the natural gas usage goes much, much, much higher. So when I'm using the air conditioning, that is being powered off of coal and natural gas for the most part, which are fossil fuels. And then in the winter, when I'm not using the air conditioning, I'm still using a fossil fuel because natural gas is a fossil fuel, of course. So these are the key devices that we're trying to focus on for people. It's stuff in the home. Manufacturing is still going to be heavily reliant upon fossil fuels for decades, maybe even centuries to come, just because of what's involved. And transportation, technically, if we have enough hydroelectric dams, if we have enough nuclear power plants, if we have enough wind turbines, our energy grid could be powered mostly by these things and then power our electric cars that way, but it's difficult to say if that's going to happen or not. So transportation, we're not going to be focusing on. This entire discussion, we will be looking at how alternative energy generates electricity. That'll be virtually the case for everything. So just so we can take a look, well, what does a coal burning plant do in order to produce electricity? Well, what happens is we dump in our coal here in this, so we're going to go left to right in this picture. We dump in our coal and that is burned, and we haven't moved away from steam power ever since the Industrial Revolution, where we really harness that. That's still basically what we do today. You burn that coal, it heats up water, it creates steam. That steam is then piped through, and it makes a turbine spin around. A turbine is just a system of fan blades, basically, and that steam turns the turbine. The turbine is then connected to the axle or the drive shaft inside of an electric generator, and that produces electric current. It might sound weird that steam can produce all this electricity for us, but steam has a huge amount of power in it. An old steam locomotive could weigh something like 400,000 pounds, but it just had one relatively small engine car, which didn't burn a ton of water, really, and that was enough to make this 500,000 pound train go for miles and miles and miles. So there's a huge amount of mechanical energy there. This is an electric motor, although I don't have a picture of an electric generator. They are technically different, but they're built the same. So if you have no idea how electricity is made, inside of that empty tube, they've taken the inside part of it out. Those wires are copper. Now, if you have a good conductor, which copper is one of the best conducting metals that there is, then on the inside, what we have here is a very strong magnet. So electromagnetism, we've known about magnets and electricity forever, but it wasn't until the 1800s that we figured out that really they're connected. You can use electricity to generate a magnetic field and vice versa. So what these things do is you get that drive shaft spinning, and that spins the magnet, and that creates an electric current. Now, electricity and magnetism, there has to be movement associated with that. They won't create electricity if they're just sitting there, but if you incorporate some movement into there, then it will work. So that's how virtually all of these, or the majority at least I should say, of these alternative energy forms and fossil fuel electricity generating forms work. They're just trying to get an object to spin like this. In the last video we watched, or maybe 2 videos ago, that little crank that I had attached to a light bulb, same thing. That's an electric generator. It only makes electricity if it's moving. Okay, moving on. We will first talk about solar energy. Now, solar energy can be used to heat, not just to produce electricity. Of course, electricity could be used to heat, but we could use the natural sunlight for heating as well. The biggest advantages to solar energy is that it's free. Once you have the solar panels or whatever in place, they operate totally for free. They aren't taxed or anything like that. They don't produce any waste. They're non-polluting, and the maintenance is extremely low. You can leave solar panels alone for the most part. Hopefully they don't get vandalized or hailed on. But if you just clean them, if they get dirty or they get leaves on them, they're not soaking in sunlight, so they need to be cleaned. But an air conditioning unit or a central heating unit or things like that in a home typically need to be replaced. A water heater maybe or something like that would need to be replaced more often and would cost more to replace, more than likely, with quite a lot of solar panels. The drawbacks to solar energy is that it's only usable during the day. So if you live pretty far away from the equator, this just simply isn't going to work. Where we live here at 45 degrees latitude, we're halfway to the North Pole from where we live. Now, in the wintertime, we might only get something like 10 or really 9 or 10 hours of daylight. But so the amount of time that we could use our solar panels drastically cuts, but it's actually worse than that, because your solar panels get more efficient the more direct the sunlight is hitting them. So in the early morning and late evening hours, your solar panels, the light that hits them is basically bouncing right off of them and hardly producing any current at all. Now, if you live much further north than what we do, solar panels are a terrible option because for so much of the year they're not going to be producing energy for you or generating electricity for you. That it's just not a great option. Now, luckily, it's pretty far north that you'd have to go, quite a ways north. You'd have to be all the way in Alaska for that to not make sense for you to do. The other problem that we have was, let me see if I have something here. No, I don't. That's weird. The other problem with solar panels, I forgot to add this, is that for the most part, most people have jobs, or if you don't have a job, you probably like you guys and you're in school for most of the day, right? So at home, from the hours of, let's just say 8 in the morning to 4 in the afternoon, well, that's peak solar energy hours, right? That is the peak time where your solar panels could be collecting electricity or making electricity. Well, nobody's home to use it. All the lights are turned off. Most of the devices are turned off. So this electricity is sort of being wasted. And right now, we don't exactly have great methods of storing that electricity. If we could capture that electricity throughout the day while you're gone, and then you could come home and use it, that would be perfect. And there is a program there is some technology for that. I'll get into that in a little bit. So anyways, these are solar panels. We all know what solar panels look like. You've probably maybe never seen them before. I have only seen solar panels a few times. Nobody around here really has them. But there we go. Solar has gotten incredibly cheap and much more efficient just in the last couple of years. So 10 years ago, there weren't very many places on Earth where it would make sense to have installed solar panels. But like computers, it's gotten so much better quickly that what this map shows is what would be the payoff in terms of energy production for, buying solar panels? Like, when do you get your energy return on that? And we can see here in Europe, at worst, it's going to be less than 3 years for the most part. And that's actually really good because solar panels may have a lifespan of around 30 years or so. Now, it should be added here, if we look at London, the UK, and Ireland there, you'd be surprised to know that that is much, much farther north than we are here. In fact, it's around 500 miles farther north than we are. So they do experience very short days in the winter time. The UK is about as far north as right smack in the middle of Canada is. And even though that they do experience quite a lot of time of the year where there's not a lot of sunlight, it's still, the payoff is pretty good. And you can see the farther south you are, the better your payoff is, obviously, because for more of the year you're exposed to more sunlight. So these are Tesla, which they have a space program, they build cars, and now apparently they're solving our energy needs too at home. So these are battery packs essentially for your house. What they do is they would hook up to your solar panels, and during the day when you're at work or when your kids are at school or whatever the situation is, the solar panels feed a constant supply of electricity into these batteries, and they are extremely large batteries with high capacity. So when you come home and your solar panels cannot give you a direct electric feed because the sun has gone down for the most part, you have this stored up energy that you can use. And I actually have their website here. They have a slightly different design here than they do in my thing here. But potentially if you have, I don't know if this is based off of one or two, but if there was a blackout, maybe you could go an entire week. You'd probably want to be smart and not use the TV very often, because what you need is to be able to cool your home or heat your home and to like have your refrigerator working, right? TV can wait. But this is never mind solar panels and alternative energy. Blackouts, they're very rare, but they do happen. This is a rather smart idea for any of us if it could store that much energy. They are expensive, but they can potentially last for so long that with the solar panels, if you're not paying a monthly energy bill, after so many years, these things will start to pay for themselves. So here in this image, we can see here, those are solar panels, and they're constantly feeding electricity into the device, which is here. And then you come home where it's dark. And yeah, your solar panels aren't directly giving you any electricity, but your battery pack is. And if we look in the interiors of these things, yep, it's really simple. It's just, I don't know if they're lithium batteries, but it's just a gigantic battery pack with only a couple other things in there. Very simple, very low maintenance. This kind of device does not have a single moving part inside of it. That's the other great thing about electric cars and electric motors. They have very few to no moving parts. A solar panel has no moving parts whatsoever. They just sit there. Anyways, solar panels are made of what are called photovoltaic cells. And I really don't know how they work, but the sunlight strikes them and it basically acts as a weak battery and creates a constant trickle of electricity. But I said earlier, we don't necessarily need to be making electricity. Solar mirrors, oh, I'm sorry, I got ahead of myself. But we can also reflect light and concentrate that light to a tower, which if you concentrate a lot of sunlight with mirrors, it gets incredibly hot. So this is just another way of making steam. This is what I was trying to say earlier. A solar collector is basically a black box that can go on the roof of your house, and it can trap enough heat to, you have to live in a place that's very warm all year round, but it can trap enough heat to heat water, for example, which is a very significant use of either electric heat or natural gas in homes, is heating water. And simply a well-built house can take advantage of sunlight and then be less energy dependent. So that's another way we can harness or take advantage of the sun. So here's sort of a diagram of a photovoltaic cell. And again, I really don't know how they work. I know how batteries work. It's a flow of electrons through the battery, and they go dead when the electrons are evenly dispersed. Somehow, these photovoltaic cells are able to make electrons basically be in constant motion, and that's what causes the constant trickle of electricity. It's very little electricity, granted. That's why you need to cover a very large area of your roof with them, but the technology is getting better and better. This, I think, is in the Mojave Desert in the United States. So these mirrors here, these are all on motors. So this is quite a lot of infrastructure. But these mirrors are on motors so they can follow the sun, so that they can constantly bounce the sunlight to the top of that tower, which is so bright you really can't even see it. But inside of that tower will be a lot of water, and that water is being boiled, and the steam from that is used to spin a generator. So in desert places, this is a great way of making electricity. This is sort of a diagram of what a solar collector looks like. I don't have a picture of one on a house, but you can Google that and see it for yourself. And then, as far as intelligently designing your house, here in the Northern Hemisphere, because we're away from the equator, you can see this is sort of how the sun's position changes throughout the year. The sun is always towards the south. So it's really never directly above our heads from where we are. So if your house has very large windows on the south side, which if your house is built on the south end of the city block, it should have that design to it. Otherwise, the people that built it didn't really know what they were doing. So this means, like in the winter, you can, if you just leave your windows open, the sunlight will come through the glass, and solar, like UV radiation, is absorbed and collected that way. So you will require to burn less natural gas for your heating or use the electric heaters in your home less often. Similarly, if you live in a where it's very hot. Like in my house, I have south-facing windows that are really big, but I have blackout curtains that I buy, and it's pretty amazing. If I don't have for a little while, I didn't have these blackout curtains, and on really hot days in the summer, the inside of the house would get to 80 degrees by like 10 or 11 o'clock in the morning. Whereas now, when I have these blackout curtains, I can go until 3, 4, 5 o'clock in the afternoon before I even have to turn the air conditioning on. So they work very well. All right, a little bit more on solar energy. The top 5 countries ranked by solar consumption are Germany at 7.5%, Italy at 7.7%, the United States at 2%, Japan at 5.9%, and China at 1.8%. Now, Honduras generates 12.5% of all its electricity needs from solar, which is higher than any other country. But that's just the percentage of their electricity that they get from it. The total amount of electricity generated is much lower than other countries which are more industrialized and have higher populations. So what we mean here is China, although they get less than 2% of their electricity from solar, they have the capacity to produce 43,500 megawatts, whereas Honduras's entire capacity is only 391 megawatts. So that's just not even close how different these are. So when you look at percentages versus total consumption, that's where it gets much different. All right, moving on to wind. Historically, we used wind to travel, and today we use it, I mean, if you want to count people that have sailboats, sure, but that's not very many people. We use it, almost all of our harnessing of wind energy is from wind turbines. The inside of that wind turbine is an electric generator which spins with the blades to make electricity. So again, we're making things spin around. The solar panels didn't do that, but from here on out, we will be doing that. Wind energy has by far been the fastest growing alternative energy method in the last 10 years. It has absolutely skyrocketed. When I was in high school, which was only like 10 years ago, that was my senior year, it was 10 years ago, you really around this area saw almost no wind turbines at all, like hardly any. And I mean, today they're absolutely everywhere. It's crazy. I drove this summer from Sioux Falls to this town about 100 miles east of Sioux Falls in Minnesota. And for 50 consecutive miles, we saw wind turbines the entire way. It's really crazy how much they've grown. So this is sort of the inside of a wind turbine. Nothing too special, just an electric generator, and down through the main shaft of the wind turbine will be the wires and everything to connect it to the grid. So here's the total share of a number of alternative energy sources. I'm not sure why nuclear isn't on here, but it's not. But if we look at wind, that's the green, and you can see that it's basically non-existent until the 90s, where it's just an absolute tiny sliver. And then just in the last 10 years, you can see that its width or whatever, which shows its total share, you can see that one has grown more than any other by a long ways. So we are adding more and more and more wind capacity in our country. It has sort of started to level off a little bit. You can see here, these are from the exact same years on these graphs. So if you look at from 2012 to 2013, you can see we barely added anything. Well, you can see in the bottom graph, yeah, we didn't install anything either. So the top is the overall capacity. The bottom is how much new or how many new wind turbines we built, and then therefore how many more megawatts are produced from that. So the top is total, the bottom is growth from one year to the next. So from 2012 to 2013, we didn't lose any wind turbines or anything like that. We just, I don't know why this is, but we built very, very few of them that year for some reason. In the United States, as far as wind producers, Texas leads the way with something like close to 45,000 megawatts, which is a huge number. Texas is one of the biggest states. and it's a pretty flat state, not bothered by lots of mountains or anything like that. So they got quite a large area to spread all that stuff around. Iowa, number 2, which is pretty surprising. South Dakota, where we are, we rank number 17, so just so you know. And Connecticut and North Carolina, those are the only 2 states that do not produce any electricity through wind, which is kind of surprising. But they'll get there one day, maybe. The drawbacks with wind power is that the supply is intermittent, which means it comes and goes. And the infrastructure and land use, the demands for that are gigantic. So back to the first thing, the wind is not always blowing. Most wind blows during the day, which is luckily when we need most of our energy or electricity, so I guess that works out. But yeah, it comes and goes at random times. Getting back to the infrastructure needs, it takes around 550 tons of iron and steel to produce a megawatt of power from wind. By comparison, it only takes 34.3 tons of coal to do that. Or I'm sorry, it only takes 34.3 tons of iron to get a megawatt by burning coal, and only 5.2 tons of iron and steel to generate a megawatt of electricity by using natural gas. Now, the reason for that is pretty simple. You have a coal-burning power plant, it stays put. Once it's built, it's built. And for decades and decades and decades, you can ship in new coal and burn it right there. Well, the wind turbine, I mean, those things are enormous. They're huge, and they take up a large area. And each one, it's self-contained. It relies on the wind, so the need for materials is much, much greater. I'm just going to speak about this for a minute. Other drawbacks that have been listed are that wind turbines also produce a lot of noise pollution. That's pretty much just a scare tactic. I know people that live very close to hundreds of wind turbines, and they never hear them. It's never complained about. You will hear people complaining about it, but I think it's a non-starter, honestly. And another thing is they do kill some birds. I used to have these numbers in my head, but I have forgotten them. But wind turbines kill something like, I want to say it's around 30,000 birds a year. In fact, I have the internet, so let's just look it up. How many birds are killed by wind turbines every year? Oh, wow, I was really wrong. So North America, so it's about 10 times more than I thought. Now that is a big number, but domestic house cats kill something like 3 billion birds every year. Billion. And through hunting, we kill millions and millions and millions and millions of the things on purpose. And with our cars, we kill millions and millions and millions of birds every single year. So yeah, it's too bad that birds die, but we're not gonna stop driving our cars, and we're not gonna ban hunting, and we're not gonna get rid of all of our cats, I don't think, anytime soon. So that's another one that's just a non-starter to me. If anyone says that, pull up some statistics on how many birds are killed through hunting or even agriculture. We farm chickens and stuff, and we kill them by the tens of millions for that. Anyways, moving on to hydroelectric power. This takes advantage of flowing rivers or bays that experience tides to produce electricity. So what we do is we build a dam, and it converts the high potential energy of the reservoir of water behind it into electricity by having that water, again, spin a turbine. So there's no steam being made, but the flowing water has, if you've ever stood in a fast-flowing river, you can feel just how much power they have. So hydroelectric has, for a very long time, it's basically always been the dominant alternative energy producer, and it probably will be for many decades to come, maybe even a few centuries to come. The only thing that really stands the best chance of overtaking hydroelectric is nuclear power. So here's that graph from before, and you can see hydroelectric, yep, it's had the biggest share. Now recently, with wind, And solar is not very big, but it's growing. Wind has really gotten into the business of hydroelectric, but wind might be stalling out in the next several decades. It will continue to grow, but we might sort of hit peak wind power. So here's a dam. This isn't the Hoover Dam, but this is a dam in America. I can't remember which one. And we can't see the internal guts of the dam, but I do have a picture for that. But right there to the left of it are, I don't really know what those things do, but next to power plants, we have all these what kind of look like telephone towers, poles, or whatever you want to call those. And that's regulating, I guess you would say, the electricity and sending it out. So here's a really simple cutout of what a hydroelectric dam does. Now, most of the dam, the bulk of it, they're made of concrete, obviously. The majority of the structure is just to hold the water back. So we have to lift that water way up to give it potential energy. It's really just a small, relatively small room inside the dam where the actual electricity production is taking place. But here's the inside of the Hoover Dam. So those are its electric generators. I don't know what they look like on the inside. I don't have any pictures for that, sorry. But yeah, here we go. That's what they look like. This is the largest dam in the world. It's called the Three Gorges Dam, which is in China. And it's 1.25 miles across. The Hoover Dam, by comparison, is not even a quarter of a mile across. This dam is straight across, whereas the Hoover Dam, dams like these are curved, and they curve backwards into the part of the river that's lifted up. And that's because if you curve it, it's much stronger. So in reality, it's because I followed the curve when I measured 0.22 miles. So it's actually only 0.16 miles across. Now this dam in China, this structure is just unbelievably huge. The amount of concrete that is in that dam there's more cement in there than the entire country of the UK uses for all of its building projects in a year, to give you an idea of how big that is. It's gigantic. Tidal power, what happens is you can do it in different ways. You can build kind of what's like a dam, and then it fills up with water, and then as the water drains out, in this example, it just drains out fairly slowly and is used to generate electricity, the same way a regular dam does. But nowadays, with tidal power, we don't really need to construct a barrier. We can basically put underwater windmills there, and because tides flow in and out of bays, that the movement of the water will simply turn these things. Now, I imagine it turns them pretty slowly, but tides are constant, whereas the wind is not. So this is sort of I don't know how efficient these are, but in theory, by looking at it, we can see that, yeah, it's probably a fairly constant way to make electricity. The biggest advantage to hydroelectric, why it's been so successful and popular, is that the water is always flowing. It's not the case with the wind or with the sun. It's always there. And because when you build the dam, it's self-contained. We don't have to ship in any fuel. Like if you burn a power plant, you have to ship in the uranium or the coal or the natural gas or whatever. But the dam doesn't, which means the electricity made from it is pretty darn cheap, which is really good. The disadvantages are that we can only build so many dams. In the United States, there's virtually nowhere left in the country where we can build dams. There are probably a few spots, but it's pretty much taken up. And for that reason, really for that reason alone, that's why hydroelectric has been static in the US for almost 50 years. We'll go back to that picture and you'll be able to see that. Worldwide, hydroelectric accounts for around 6% of global electricity. I don't know what it accounts for in the United States off the top of my head, but you can look that up. But we think that it has the potential to double around the world, but not much more than that. The other problem is you just can't do it everywhere. You know, in Nebraska, maybe there are dams in Nebraska. We have a few dams at what's it called, Fort Thompson. There's a dam. There's also a dam right next to Pier. But that's about all we can get. In other states like California, they can build lots of dams because they have high mountains and lots of streams that have a lot of energy in them, so they can take advantage of that. The other disadvantages associated with hydroelectric power, those are environmental concerns. And when you build a dam, that leads to an extreme rising of the river channel upstream, which clears out all kinds of habitat, obviously. And if people live there, then, well, they have to pack up and move all their belongings. Their house is going to be flooded, obviously. And the other thing is, for people that live downstream from the dam, a dam does not pollute. That would be another advantage I should have put in there. There's no pollution with dams, but the amount of water that flows downstream is severely reduced. For example, the Colorado River, which the Hoover Dam is, that's the river that goes through the Hoover Dam, that actually doesn't reach the ocean anymore. It has for forever and ever, but now there are so many dams built on the Colorado River that the water doesn't actually reach the ocean. The river just kind of dries up, which is a little weird. So here's a satellite picture of, I'm going to do this so you can see my mouse here. Right there is where the Hoover Dam is. If I zoom in, you can't really see anything because it's all grainy. But that's where the Hoover Dam is. This is Las Vegas over here. This is what's called Lake Mead. Now, before the Hoover Dam was built in the 30s, this lake did not exist. So look at the width of the river down here. That's how wide the Colorado River was all throughout here. Now, you can see just what we've done to this area. I mean, we've totally flooded it. Now, around here, it's all brown. So we probably didn't really kill a lot of habitat, and there wasn't anybody living here when this was built. Las Vegas didn't even exist, really, before the Hoover Dam was built. It was there, it had a name, but it had a tiny population, whereas today Las Vegas, it's full of lights and everything. This right here, Lake Mead, is the largest reservoir in the country. This holds more water than any reservoir that we have. Now, down the river from the Colorado, or down the river from the Hoover Dam, I should say, this is pretty close to the ocean right here. This is a town in Mexico. I don't know what it's called. But you can see that's the Colorado River, except it isn't the Colorado River because there's no water there. 2014, as far as I know, was the last year that water from the Colorado River actually emptied into the ocean. And that was the first time in 16 years that it had done so. Now, going back to China, here is before and after pictures of that Three Gorges Dam. So you can see that there's quite a lot of trees have been cleared out, and now there's a city there. So if you build a dam, you can make electricity and people can live in this area, which is good for people. Is it great for trees and animals that live there? Well, I guess not, but maybe that's okay. But the more often you do this, and in China it's a much bigger problem, the more often you do this, again, the less water flows downstream. So China has a gigantic population, but many of its people still live very, very simple agricultural lives. And they obviously are hugely dependent on water. And China has a communistic government, so yeah, they're capitalist, they have a very large economy, but they are still a communist country, which basically what it means for them is when the government says that they're going to do something, you really don't have any choice. You're going to cooperate with the government or be arrested or something like that. So these people that live down the river, they don't really get a voice in their government to say, hey, look, you're going to destroy our way of life if you do this. The Chinese government says, too bad, so sad, Charlie. You got to pack up and move or deal with it. And similarly, with people that lived in this area where it was now flooded out, they don't get a voice either to say, hey, you're going to destroy my house. You could, the least you could do is pay us for it. And there was some compensation, but not nearly enough. All right, moving on to geothermal energy. So, just to reiterate, coal, natural gas, nuclear energy, these all generate electricity by producing steam. Well, geothermal cuts out the middleman. It's the application of naturally occurring steam, so we don't have to burn anything to get our steam. And we can use geothermal for making electricity or just directly for heating. And I don't really have too much to say about geothermal energy, but the countries that produce the most geothermal energy are those that tend to have a large number of volcanoes. And this makes sense because there are very few places on Earth where geothermal energy can be used. Now, if you live somewhere where there are volcanoes, that means that the magma below your feet is much closer to the surface than it is in other places. So that means that the crust below your feet is much warmer at shallower depths, and there's groundwater all over the planet. So this is what makes the steam. The drawbacks to geothermal is that there's only so much steam trapped down there. I don't know what the average lifespan of a geothermal plant is off the top of my head. Sorry, you can look that up. And there are very few regions in the world that have any kind of access to geothermal reservoirs. In fact, there are only 12 countries in the entire world that have a capacity for what I would call a reasonably large amount of electricity generated by geothermal. And it's really not very much. The top there is the United States. I'll actually wait to explain that to you here. So just to show you how small of a footprint geothermal energy has, the state of Texas alone produces 3.5 times more megawatts of electricity from just wind than the entire globe produces from geothermal energy. So it works very well for some people in some locations. Like, by all means, if you've got it, we should use it, but it's not the answer for the future by any means. So geothermal is the right in the middle there, directly underneath the wind. So it's pretty narrow margin. It's been about the same width. If we look, it first really pops up in 1990, it looks like, and it's pretty much had the same share for that entire period. So it's really not a growing sector. Here's an example of what a geothermal plant looks like. This is in Iceland. And really simply, I've cut away, or this picture has cut away the turbine and all that, but it works exactly the same as the coal power plant, just without any, without having to actually burn anything in there. The top geothermal energy producers in the world. So United States number 1, Philippines, Indonesia, Mexico, New Zealand, Italy, Iceland, Kenya, Japan, and Turkey. Now, again, what I was saying, lots of volcanoes. Actually, before I do that, I want to look at this because I was talking about this. The United States, and don't pay attention to these labels up here, the United States has the capacity to produce 3,500 megawatts of electricity. That really isn't very much electricity. And then the bottom end here, which is Turkey, they only have the capacity to produce about 400 megawatts of electricity from geothermal. That's really, really a small amount of electricity in the grand scheme of things. But anyways, the other thing I was talking about is countries with lots of volcanoes. So the United States actually has a pretty decent share of volcanoes in it, if you didn't know that. The Philippines is an island, or it's a system of islands in the Pacific. All of the Philippine islands are made from volcanic processes. Same with Indonesia. The famous Krakatoa, the biggest eruption in hundreds of years, in many hundreds of years probably. Yeah, that's an entire volcanic archipelago of islands, just kind of north to northeast, or northwest, I'm sorry, from Australia. Mexico also has actually a few volcanoes in it. New Zealand is entirely volcanic. The whole island system is made of volcanoes. Italy famously has Mount Vesuvius. That's a volcano. Iceland literally is a volcano. It's actually a bunch of volcanoes, but everywhere you stand on the surface of Iceland, you're standing on a volcano. It's just like Hawaii in that sense. Kenya has what's called a rift valley, Mount Kilimanjaro. There are many volcanoes in Kenya. Japan, the entire island system of Japan is all volcanoes. Mount Fuji, for example. And Turkey has, well, I don't know of any volcanoes in Turkey, but it probably has a few of them. Anyways, moving on. To nuclear energy. Now, nuclear energy, we saved this for last. Nuclear energy, more so than any kind of alternative energy, is probably the future because it shares so many of the exact same advantages with fossil fuels, except that its energy density is literally millions of times greater than fossil fuels. So excuse me. Anyways, the process of making electricity with nuclear power is the exact same as a coal power plant. The uranium and thorium that are used, they don't burn, but they naturally release a lot of heat because they are radioactive, and they will do so for long periods of time. And that heat, you keep these bars, these radioactive bars, in water, and it heats up the water and makes steam. Boom. As if we would compare this to the diagram at the beginning with the coal power plant, they're designed almost exactly the same. So there, let's take a look at that for a second. This is a picture actually on the inside of one of the reacting cores. So I'm not sure if that glow is from the material. I really don't think it is. I think that's just light, but this is sort of what they look like. Now, I can't tell you what anything in this picture is, but I can tell you that it's the inside of a nuclear reactor's core. This GIF here. So what the heck is going on with radioactivity? Well, on the nuclear level, on the atomic level, I should say, it's a gigantic chain reaction. So what's actually happening is that uranium is being split apart. So here a neutron strikes the nucleus of an atom and it breaks it apart. Now, to split the atom requires just an unfathomable amount of energy to do, and it releases a huge amount of energy. This is how atomic bombs work. They're so energetic because it can create energy just in huge proportions. That's what E equals mc squared actually means. Now, once a nucleus is split apart, it produces or it releases 2 new electrons plus the original one, and those will go and bombard 3 new nuclei. So this is why it's a chain reaction. This is also why it's incredibly important that nuclear power plants have systems and regulations and controls. Because you can see I just went from 1 to 3. 3 will become 9. 9 will become 27. Well, you can see that in fractions of a second, this could cause the entire uranium core that you're dealing with to split apart, which would be really dangerous. That's when a nuclear meltdown happens. Now, the materials that are inside of nuclear power plants, they can't explode. So they're not like nuclear bombs in that way. Even though nuclear bombs can be made with uranium and power plants can too, there are different isotopes of uranium, and they don't all have the same physical properties. So there is no radioactive substance used in power plants that can blow up. It's not possible. So nuclear actually provides a pretty respectable share of electricity in the United States. It's around 19%, but it hasn't grown in many, many, many decades. And again, the reason that nuclear is such a good option is because it has all the same advantages of coal. It's a solid, so it's really easy to transport from one place to the other, and it makes electricity pretty much in the same way. We know how to build coal plants, so we know kind of fundamentally how to set up nuclear plants. The major difference, though, and this is a good difference, is that radioactive isotopes are millions of times more energy dense. A 12-foot uranium rod lasts for 6 years in a nuclear power plant. In 6 years, a nuclear power plant will burn through millions of tons of coal. If it's well, maybe millions of tons is an exaggeration, but definitely many hundreds of thousands of tons of coal. I don't know the exact figure. You can fact check me on that. But that's a huge advantage. It's just one relatively small piece of uranium, and it lasts for 6 years. We looked at this graph in the last lecture, or maybe it was the first lecture, I don't remember, but there's uranium and thorium at the top, and look at their energy density compared to coal. It's huge. Now, in practice, because we have to use the uranium to make steam, and because we lose some of that energy because of inefficiencies, it doesn't literally work out to be exactly, if you would divide these numbers, it doesn't exactly work out that way, but it is thousands of times more efficient per unit of weight than coal, which is very good news. So here for the globe is the growth of nuclear power by terawatts, and you can see that it really isn't growing all that much. It was in the 70s. And then all of a sudden, if we look at 1986, 1988, that's the point where in most places, except for Asia, it pretty much flatlined. And actually, if we look at Asia, it's kind of hard to tell, but those bars, the ones in 2016, are really not any bigger than the bars in 1996. So, gee, I wonder what happened in the late 80s to make people, to stall the growth of nuclear power. Oh yeah, Chernobyl happened. So they were doing some safety tests. They were going through a scenario where they were trying to test, hey, what would happen if part of the reactor was not working right, and we had to like not fix it, but like they were just trying a different method. But they were doing it with like live materials, and they didn't have the right fail-safes put in place, and the chain reaction very quickly got away from them, and then it exploded. Now, I know I just told you that the uranium literally can't explode. The uranium did not explode. In fact, no, that's not it. That is a picture of the uranium right there, that glowing orange blob. That is all of the uranium. It might have been thorium, but I think it's uranium in that power plant. So no, it didn't blow up, but the reactor itself blew up. And this was a really terrible disaster. Many people lost their lives, and many people, many hundreds, many thousands of people actually developed cancers after this. So it really put a dark stain on nuclear energy. But this is the only incidence in the entire world where nuclear energy has claimed any lives. There were other instances. The most recent one was Fukushima in 2012 in Japan. Nobody died from that. We don't know if anybody has developed cancer from that or not either, but there hasn't been any studies that show it had. And then the United States had one also in the 70s, I think it was, at what's called 3 Mile Island, so you can look that up for yourself. This was just completed only a couple years ago. This is the tomb, the sarcophagus for the reactor. So if you see that tower right there, that tower is still, it's in this picture too. I think that's the same tower. And they've covered it up. Now, that is not designed to keep the radiation from coming out. What it's actually designed to do is keep like rain and the weather from going in there, because if water got into here, then the water could wash up these leftover radioactive, because this sort of pollutes everything around it. It makes everything around it radioactive, not just the substance right there. So that was a concern that, the wind and especially water from heavy rain could wash around all these radioactive particles. So that's just to contain the radiation. So with regards to disadvantages, the fact that nuclear power plants use radioactive isotopes is not really a disadvantage in the same way that we know oil spills happen, but the benefits outweigh the risks. Yes, Chernobyl happened, and a couple other disasters have happened, But we've had far more in terms of number oil spills. I mean, it's not even close. We've had thousands and thousands of those. And yes, they are disasters, but what fossil fuels and what nuclear energy allow us to do to have electricity to make our lives better and safer far outweighs that by quite a bit. The major drawback is that the infrastructure and maintenance costs of nuclear energy is much higher than the comparable coal or natural gas. Now, it's just basically a rule of economics that the more you use and implement and develop something, the cheaper it will get to use. And so it's really a shame that nuclear energy has stalled by so much in the last several decades, because it will inevitably get cheaper, and it's just too bad that it's not already cheaper, because we could be solving a lot of the problems we have right now with nuclear energy.